We're moving from evil megacorps in a cyberpunk environment to actually Max, who's going to talk about Neuropunk. These are the closing remarks of today's session. Max is obviously, the instigator of all of this. You coming to the Institute of Artificial Intelligence. I was talking to somebody earlier today that you were kind of like the first electron that caused the chain reaction. So it's fitting that Max also closes today's session. Again, most of you know Max already. Please take it away. Oh, what do you need that for?
Okay. Hello. So before I start my presentation, I want to do some quick recap that I'm really happy. Though we are just small number here at the moment, but mainly I'm really happy that we managed to do this interdisciplinary session that was really crowded at some moment, and people were standing rather than sitting because we didn't have free spaces anymore. So I'm really happy that we've done a lot of talks, starting from linguistics applications and some neuromorphic devices, hardware, software, and quantum computing, and all this crazy science that we call that stuff that we managed to integrate here. And that is absolutely fantastic option to have all of you here. Thank you very much for coming. Thank you very much for attending, and that's really a pleasure to have all of you here today. So I'm going to be quick, and my timer is not counting anymore. Yeah, I'm out of time. Okay. So we've been talking about advantages, disadvantages. Why we're talking about disadvantages mainly? Not because we don't like AI, not because we don't like neural networks, not because we don't admire the progress, blah, blah, blah. But that was already said many times. We're focusing on problems because there is something that we can improve. And we hope to improve in nearest future. And possibly in how many years, Alexei said? 7 years, right? So hopefully that will solve all that. So we have problems of digital. Digital, I call that digital because I think, for me, neural networks, that's why I don't distinguish neuronal and neural network, because in us, we have neural network. It is natural, right? Biological. That's why I call that neural network. No, it's non-digital, and we know that it's not digital. I like to call it spiking neural network rather than neuronal, because for me it's the same thing. It's just different implementation, if you like. So, but digital technology, as I said many times here, you have to pay for it. And it has, and we know, now we can compare, and we know that it has problems. It consumes terawatts of energy. Why it consumes terawatts of energy? Because it has to process terabytes of information, and you have to pay for processing. And then it's still fragile. We know that it's still fragile. It's not that good. Sometimes it's good. Georgie said that it's good. Yes, but again, we know the advantages usually because we use ChatGPT, we use Perplexity, we use Midjourney, we use some other technologies that are our favorite. This is, how many courses are here? 1, 2, 3, Jordi, 4 authors of this paper are here, and I'm really happy that we are here. And Alexei was pointing on that either, and there are a lot of speeches pointing on that energy consumption. And I was delivering the interview to Euronews about energy consumption again. This is a big problem now because we now can compare these big LLMs to the brain. And we're not just doing LLMs, to be honest. We're doing much more things, sometimes interesting, sometimes boring, but we're doing more things than just doing LLMs. And no LLM could come here and deliver the speech. And we've done, all of us, done that. That is impossible for this technology. And so what we see here Oh, I can use a pointer. No, I cannot use pointer. Okay, so to the left corner, and I just want to remind you and point your attention that it's logarithmic scale. To the left upper left corner, we have these digital technologies using artificial neural networks. I don't remember how many. Oh yeah, you can read it here. ResNet, it's really popular, LSTM and transformers that is used actually in ChatGPT, and it's upper left corner. So yeah, they have useful functions, but we have to pay for that. And here we have the brain. I mean, not the brain, the neuron. It's actually the synapse of the brain. So it's really, really, really energy effective. So why it is that? Okay. Oh, okay. We have this beautiful slide here, and I'm happy that the author is here either. So, well, we can compare in chocolates. I really like that. We can compare in chocolates. So for the brain, we use 1.5 chocolate bars, which is 150 grams. And to feed ChatGPT, we have to spend 1 kiloton, right? How many years we have to eat that? You can count. The guys who have better arithmetic than I do. So comparing brain in electricity, right? Not in calories, in electricity. Though brain is a light bulb, so that was said many times here. And what is the ChatGPT version 3 is here in Sweden. So this, I assume this light bulb was made in Sweden either. So this is energy effective. This is only 20 watts. So this is not in favor of artificial neural networks, but this is potential. This is what we can do. This is what students can do, what we can do at the moment. So we can make it much, much, much better. And we have the potential in orders of magnitude, like from 6 to 8 orders of magnitude. We have this potential. So the reasons of that, so we have this comparison. And so the reason that we have to follow the rules of the nervous system, follow the rules of brain, if you like. So, and if we don't follow the rules, you have this inefficiency then, okay. So, we've been talking about diversity, we've been talking about feedback loops, for example. Feedback loops are really key point that hasn't been much addressed in the literature. And that's TDP spike time dependent plasticity. They have interplay of these phenomena. So feedback loops by itself means that nervous system is capable of generating the information in place in time when it's needed, instead of having terabytes of the information that we have to feed in for the artificial neural network, because it feeds forwards. It just get input and output, and bye-bye, that's it. So it doesn't have feedback loop, so it cannot do the self-learning, it cannot self-correct, and cannot self-organize. And self-organization, again, it's a key concept and key, key approach, if you like, to build the biological system. Biological system is built on the self-organization. And even going into the details, even proteins are self-organized and so on and so forth. We have to employ these approaches that is not used mainly in industry. This is one of the key points. As for memory strip devices, so there is the other advantage. So mainly energy is spent to switch the state rather than control of the system. The ineffectiveness of feedback propagation is that bad that to update the weight of one synapse, you have to update all of them. And this is really bad algorithm, and I don't care if you assign the Nobel Prize for that, this is really bad. Because ineffectiveness, if you think of the worst case, think that in your brain, if you want to update, if you have to update one weight of one synapse, you have to update all of them. It's 10 powers 15. And you have to plug power plant here. Definitely, I don't have it, and you don't have it. We don't have it. We have much less energy, and that was, again, measured like 20 watts only. So we have a nice example of really effective system that we have, And once I was asked by one professor of, I guess, Brown University, what if you don't have this example? I mean, nervousness, he was addressing what, because I was like, the thing is that the story started, I guess, from Alan Turing. And he said, like in 50s, that we don't have to mimic brain to create artificial intelligence. And we are like trying to not to mimic. We are trying not to mimic because he said he was genius. Yes, he was genius, but he's outdated, honestly. He's outdated because we have a lot of systems that are not like mimicking, but we are getting inspiration more and more time. Even computer was inspired by brain. And then we have neurons, neural networks that, again, inspired by neurons. Neural networks inspired by neural networks that we have, and then we got convolutional neural networks inspired by visual cortex and so on and so forth. We have this analogy all the time. So, and we're but we're still like prohibited to look in the textbooks of neuroscience. So that's a bit strange for me. It looks like not really logical thing. And okay, so I want to introduce this term spiking technology. And I want to call this spiking technology rather than analog technology because it has special rules and we know those rules. And so, yeah, Victor, this is about you again. Yes, second time during this conference because Victor, he's the inventor of memory-assisted device and he was the first one. Yeah. That was mathematically described by Leoncio, and then you have made this first implementation of the hardware, and we have discussed that. Okay, I'm going to skip that because that's already been introduced by Victor, and I'm going to go to this really interesting experiment that we have done with Victor with the feedback loops. Why I'm so keen on feedback loops? Why I like the feedback loops? Because that was actually Victor's idea. That wasn't my idea, and I'm introducing his idea. So we tried and we implemented the part of the spinal cord, of the injured spinal cord of the rats. So you can see only 1, 2, 3, 4, 5 neurons here with a feedback loop that comes from the feet of the rat back into the spinal cord. And only 2 of them have the learning capabilities. And you see that on the top there are only 2 neurons that has memory-assisted devices on board. And then, so this is the input information. So we have this feedback loop as an input information, but okay, that was bioplausible, that was mainly organized. Like you can imagine that like a transfer of the weight from the heel to toe, and you can see 1, 2, 3, 4, the switch of the inputs, and you can see the frequencies that goes through this feedback loop. And this information needed for the spinal cord, like implemented the hardware was generated there. And so you have only this setup of 20 hertz, 100 hertz with the periods, 200 hertz and 100 hertz with the periods, and that is only input. And then at the output, at the output you see this complex pattern that resembles the rat under the rehabilitation process pattern. And that is what we called, Vida actually called that artificial skill. So you have this trained artificial skill of walking, and that was like self-organized, self-trained, and during 1 minute. And for the rat to get to this state, you have to spend 40 weeks. So that was really quick one. Yes, that was because there are a small number of neurons, minimal number of neurons, so on and so forth. But anyway, the pattern, the diagonal pattern of the training, after the training, resembles that we see in the rat. So you actually can implement the hardware, and that is just a hardware. So my point here is that you don't need software. You need a hardware. If you do artificial intelligence, and that could be really effective, but that would require your thinking, your understanding how this could be organized as a pure hardware. Because here we have the hardware. We don't have software. We don't need Python. We don't need C++. We don't need Linux. We don't have it at all. This is the limitation of current digital technology that we use heavily because it's useful, but still we can do better. Right. This is my favorite picture because it actually introduces, yeah, I have it. From the spinal cord, they have feedback loops that goes to the brain. So this is kind of hierarchy of the feedback loops that generate the information, and we use that heavily in our biological systems, in our nervous system. And that's how we train that fast, that's how that effective. This is one of the reasons. Okay. Well, this is the goal that we have to create more restive spinal cord. And there are people involved in that. I hope that we will have it. And the thing is, okay, there are, well, phase transitions and of the spinal cord that we've done as preliminary research with guys from Nizhny Novgorod. Actually, so this is the goal that we have. And I hope that we can achieve that, and I think that we can do that with the microwatts of energy, and that could be implantable technology. And we could, instead of stupid controllers, digital controllers, we could actually implant spinal cord in patients and help them do the rehabilitation processes. Yeah, and those guys actually have in digital technology, they have digital spiking neural networks. But we can do even better, we can do just spiking. And that could be, for example, used in robotics because it's used in cats. It works, and we know that it works. Okay, I guess this is the final slide here. And I want to thank everyone who take part in that initiative, absolutely crazy science, but that is paving the future of electronics, and I think that there is need to do the better technology, and we can do better. And thank you very much for listening to that. Thank you very much for attending that. I think that's it. Thank you.
So, any questions? Or are we going to get a drink? You have a question? No, just kidding. Can I have a microphone? Just hold on 1 second. Here you go, Alexei.
Thank you. This is my first question at this event, and it is about spinal cord. What is the perspective and how many years you need to create it?
He mirrored Max's question back.
So minimally speaking, so we have some parameters here, and we hope that we can actually achieve that really soon. So if 24 neurons, 24 synapses, memoristic synapses, so I think that we can do that on current technology. The thing is that we should think of minimalization of neurons rather than synapses, which is, you have the chip, and it's quite relatively small. And according to my understanding, it could be potentially implantable. We could think of make it more stable and so on. So it's durable at the moment. So what I'm saying, it's realistic to do now. And if you think of the parameters like bioplausible parameters, that number of neurons that we have here, well, I think 5 years. Like 5-7 years, you're right. So we are, well, what I want to say that we are in revolution. We are not before, we are not on the edge. We are in the spiking revolution, we are here. So it's going on, there are more people that getting this understanding. When we started in 2015, I have to explain what it is all about, what is spiking, what it means. But now everyone knows. I don't have to explain that. And everyone get this analogy and inspiration from the nervous system. And they are okay with that. There is no boundary. It's only now ahead. Artificial neural network and biological neural network. It's actually neural network.
Thank you, Maxim.
Thank you.
It seems like a good plan, and we will follow you on this way. Thank you.
As far as I could tell, your chip is done in 5 to 7 years. Your spinal stuff is done in 5. You will be right on time.
Yeah.
Thank you.
All right, thank you, everybody. It was intense. It was emotional. I mean, neuromodulated emotional. And hopefully, we'll continue this exponential growth to next year. So anyway, thank you, everybody. Thanks for coming, and let's close the show.
Thank you.